Almost all engineering design teams and their clients operate to design rules that aim to avoid water column separation and recombination. Consequently, it is extremely rare that an engineering design team needs to quantify the surge heads that would occur after column recombination with sufficient accuracy to prepare a detailed engineering design. It is, however, important that you understand how WATHAM models column separation and column recombination, and that WATHAM provides a conservative approach to the subject. To track liquid-vapour phase changes in the pipe system, WATHAM uses a mathematical technique called the discrete vapour cavity model, or DVCM for short. This is a good model when the vapour cavities are localised within a pipe, for example at the crest of the hill where the pipeline goes over a ridge. The discrete vapour cavity model is less realistic if vapour formation spreads out over a long distance in a pipeline. Let me explain in more detail what the discrete vapour cavity model means. Here we are looking at a single pipe divided into water sections. In the initial steady state conditions, the hydraulic grade line along the pipe may look like this green dotted line. At some later time after a transient event has disturbed the steady state, the hydraulic grade line may look like this. At this point in time, the hydraulic grade line is still above the pipe's obvert level. There is positive head in each water element in this pipe. Now at a different point in time, the hydraulic grade line in the pipe may look like this. Now we see some sections experience positive head, while other sections are experiencing negative head, where the hydraulic grade line is below the pipe obvert. If the hydraulic grade line drops low enough to reach the liquid's vapour pressure, what happens? Some or all of that water section will change into the vapour phase. To help us understand the discrete vapour cavity model, think about your car in your lane of the freeway again. DVCM considers your car to be a discrete compartment. The DVCM quantifies how much of your car is filled with water and how much of your car is filled with water vapour. Inside a pipe, the DVCM represents water sections with a vertical interface from the top of the pipe to the bottom of the pipe, separating it from its neighbours. In reality, when pressure reduces in a pipeline, the lower pressures occur at the top of the pipe and progressively increase downwards. In reality, phase change in a pipe is a horizontal phenomenon. This discrete vapour cavity model can't go to this level of detail. Looking at this transient hydraulic grade line with a large number of adjacent water sections fully occupied by water vapour, can I ask you, how well do you think the DVCM model works in this case? In preparing your answer, consider that in that part of the pipeline at different points in time, fractions of a second apart, you may have a mixture of liquid water, water vapour, dissolved air that has come out of solution. Develop an image of how you believe this mixture will be physically dispersed in this part of the pipeline. Think about how this mixture will move. Think about how this mixture is likely to behave when the pressure increases above vapour pressure in this part of the pipeline. In reality, when the pressure increases in this part of the pipeline, I would expect a chaotic, turbulent mix of open channel flow at the bottom of the pipe, with water vapour and air at the top of the pipe, very similar to the water in a boiling kettle. When the pressure increases again, it will take a finite amount of time for this mixture to all change back into the liquid phase. While we have air at the top of the pipe, we have a shock absorber sitting in the pipe. The DVCM doesn't allow for the presence of these shock absorbers. As a result, the DVCM can create small, rapid surge ripples as vapour cavities in individual water sections collapse. These ripples don't occur in reality. The end result is that the DVCM produces surge amplitudes after water column recombination, that is, all water sections in the pipe are now liquid again, that are likely to be higher than reality. In other words, DVCM will give you conservative engineering results.